In this lesson, we're going to continue to factorise polynomials with complex roots using a range of different methods. So our first note is that any cubic equation that has real coefficients will always have at least one real root. You can verify that by trying to draw a cubic graph that doesn't cross the x-axis at least once, and you'll find that you're not able to do so because it either starts at the bottom and ends at the top, or starts at the top and ends at the bottom. It always has to cross the x-axis at least once, which means it will always have at least one real root. Sometimes it'll have two or three. So we can find that one real root using the factor theorem. If you can find a value of x that makes the expression equal 0, then you can conclude that x minus that number will be a factor. Once you have got that real root, you can then write it as x minus a, and then x squared plus bx plus c equals 0. You can then use whichever long division method you would normally use to find the remaining quadratic. That remaining quadratic will either have real roots or complex roots, and we know that the complex roots will have to be complex conjugates. So in our first example, given that 1 minus I root x is a root of the polynomial f of x equals x cubed plus x squared plus x plus 21, we want to find the other two roots. So the first thing we can say is that because we know 1 minus root x is a root, and we can see that all the coefficients of f of x are real, we can conclude that another root will be 1 plus I root x, I root 6. So we know that there will be a quadratic factor x minus 1 minus I root 6 and x minus 1 plus I root 6. There will also then be a third factor which we can find. But we're just going to find the quadratic factor first. Now you can multiply this out however you prefer. You can either multiply the brackets or you can do a grid method. If you do a grid method, we're going to get x minus 1 plus I root 6, x minus 1 minus I root 6. So in a grid, I'm going to put x minus 1 I root 6, x minus 1 minus I root 6. I'm just going to multiply that out. So we've got x squared minus x I root 6 x minus x plus 1 minus I root 6, and then we've got minus I root 6x positive I root 6, and then we've got minus I squared times root 6 times root 6 is just 6, so it's actually minus 6 I squared, which is of course positive 6. Okay, so some of these terms are going to cancel. We've got I root 6 x and minus I root 6x. We've also got minus I root 6 and positive I root 6. So what is left is x squared minus 2x, then we've got 1 and 6, so plus 7. So from that, we now know f of x will factorise into x minus a as a first bracket and x squared minus 2x plus 7 the second bracket. Now by inspection we can just look at the numbers at the end. We can see that minus a times 7 has to multiply to give 21. So if minus 7a has to be 21, a must be negative 3, which means that the actual bracket is x minus minus 3, so x plus 3, x squared minus 2x plus 7. So that tells us that the roots of this quadratic are x equals minus 3, that's the real root, x equals 1 minus I root 6, which we were given in the question, and x equals 1 plus I root 6, which is the complex conjugate. So we've got one real root and two complex conjugate roots. This time we've got a quartic equation, so power 4. That's going to have 4 roots. We've been given one of the 4 roots, 3 minus 5i. We can see that f of x, all of its coefficients are real. So that means that any complex roots are going to have complex conjugates as well. So we already have that one of the roots is 3 minus 5i. We can immediately say that the second root is 3 plus 5i. Now, there's a possibility that 2 more roots will either be 2 real roots or it may be another complex conjugate pair. So we're going to start off by multiplying the 2 factors together that we do know. So we know x minus 3 minus 5i, x minus 3 plus 5i. Multiply that together to get us the first pair of roots. So the first quadratic root. So we've got x minus 3 plus 5i, x minus 3 minus 5i. So multiplying that out, we've got x minus 3, 5i, x minus 3 minus 5i. So we've got x squared minus 3x, 5ix, minus 3x, positive 9, minus 15i, minus 5ix, 15i, and minus 25i squared. So just cancelling out the parts that cancel, they cancel and they cancel, and noticing that that is just going to be plus 25 because of the I squared. The first quadratic factor is x squared minus 6x, that's there and there. We've then got 9 and 25, which is 34. So that is our first quadratic factor. We now know f of x comprises of the first quadratic factor that we've found and a second quadratic factor, which we need to find the coefficients to. So by inspection, we can see a is going to equal 1, so that ax squared times x squared equals x to the 4. And again, by inspection, we can see at the end, we need c times 34 to equal negative 68. That's the term at the end. So c must equal negative 2. So we can write this as x squared minus 6x plus 34. You could also do division if you wanted to. If you wanted to divide f of x by x squared minus 6x plus 34 a different way, you would arrive at the same answer. I'm comparing the coefficients. So I've got x squared, we don't know b yet, that's bx, and then c is minus 2. I'm now going to expand the 2 brackets and compare the coefficients to find b. So I'm going to start by doing x squared multiplied by everything in the second bracket. So x to the 4 plus b, x to the 3 minus 2x squared. Then I'm going to do minus 6x times everything in the second bracket. So minus 6x squared minus, 6x cubed minus 6bx squared and plus 12x. I'm going to do 34 times everything in that second bracket. So 34x squared plus 34bx minus 68. So I just need to compare any of the coefficients to find the value of b. I'm going to compare the x cubed coefficients. So I can see in the expanded answer, I've got bx cubed, I've got minus 6x cubed. So that is b minus 6. In the expression at the top, in the original cubic, I've got minus 5x cubed. So therefore, I can conclude that by comparing the coefficients of x cubed, b minus 6 equals negative 5, So b will equal 1. Okay, nearly there. So f of x goes into two quadratic factors, x squared minus 6x plus 34. And the second one is x squared. We said that b was 1, so plus x minus 2. We know that the first one went into two complex conjugate roots. We ended up with x minus 3 minus 5i and x minus 3 plus 5i. I'm just going to solve the second one to see whether x squared plus x minus 2 has real or complex roots. And we can see by factorising, that will factorise as x plus 2, x minus 1. So we've got real roots. This tells us that the original quartic equation has roots. X equals minus 2 and 1, they're the real roots from the second quadratic, and 3 minus 5i and 3 plus 5i, which are the complex conjugate roots from the first quadratic. Okay, so this is an example of a cubic where we've got one of the coefficients unknown. So we've got z cubed plus mz plus 74 equals 0. We are told that m is real, so we know that this cubic has got real coefficients. We're told that 1 minus 6i is one of the roots. We want to find the other roots and then determine the value of m from that. So first of all, we are given one of the roots, and because we know we've got real coefficients, we know that any complex roots will have to have a complex conjugate root. So we know that 1 plus 6i will be the second root. Okay, we also know that because it's got a real root, we know that all cubics have to have at least one real root. So we know it can be written as z minus a, and then z minus the first complex root, and then z minus the second complex root. We know that all of that has to equal 0. So from the original equation, we can see the constant term is 74. And we can use the brackets to help us find the third root. So because we've got minus a here, and we've got minus 1 minus 6i, and we've got minus 1 plus 6i, if we were to multiply those three together, we would get minus times minus times minus, which is minus, and then the product of the three roots. So in other words, the product of the three roots is going to be negative 74, or the negative of the product of the three roots will be 74. Okay, so we know that a times the first complex root times the second complex root will be negative 74. As I said, it's negative because we're basically multiplying three minuses together when we expand those three brackets. So using the fact that 1 minus 6i times 1 plus 6i is 37, we end up with a times 37 is minus 74, which gives us a value of a of minus 2. So minus 2 is the third root, and z plus a will be that third bracket. So now that we know the equation can be written in this form, in the three brackets, we could choose to just expand all of that, and that would tell us m, because it would tell us the full equation. So expanding it all out, we get m equals 33. An alternative to that would be to substitute in one of the roots. We know that the roots satisfy the equation, because that's what a root is. The easiest root to substitute in would be the real one. So what we could do is we could just put minus 2 in for all the z's and solve the equation from there. That would also tell us m. So if we put minus 2 in where all the z's are, we end up with negative 8 minus 2m equals negative 74. Rearranging that equation also gives us the m equals 33. So here are some notes just for your notebook. First of all, any quartic equation, that's power 4, that has real coefficients, that's got three possible sets of roots. Either all four of its roots will be real, which means it will cross the x-axis 4 times if you draw the graph. The second possibility is it might have two pairs. It might have two real roots and then two non-real roots, and the non-real roots would have to be complex conjugates of each other. The third possibility is it might have all 4 roots being non-real. In that case, it would have to be two pairs of complex conjugates. They would both come from two different quadratic equations, neither of which had real roots. So can you please complete exercise 2B on page 37?